So, what is the difference between the voltage droop and speed droop in a generator, sir?
Okay. So you're talking from electrical perspective.
So, speed droop is in the governor, sir, but voltage droop is coming KVA.
Okay. Correct. Okay, that's a good question. Voltage droop and speed droop. Well, speed is actually related to frequency, correct?
Yes, sir.
I'll just explain quickly.
Yes, sir.
Okay. So when we say droop, speed droop, we more or less link it with speed, that is RPM of the ship, RPM of the generator. Speed, obviously, when we say speed, we talk about RPM of the generator of DG. That is directly proportional to frequency. Or you can say frequency is directly proportional to RPM. So by this formula, they are linked with this formula, where N is RPM and F is frequency, P is number of poles. So poles of an alternator are fixed, that you're not changing. So that means, so ultimately what remains is that frequency and this thing are linked. Okay, frequency and speed are linked to each other. You increase the speed, you increase the frequency. You decrease the speed, you decrease the frequency. Okay, next point here is, so let me link it to the droop part. So basically what happens is droops is important when you want to run two generators in parallel. If let's say you are running only one generator, whatever may be the droop setting, it doesn't really matter. So droop is actually deliberately induced in the RPM maintaining in the RPM controller or speed controller, or you can say frequency controller, because that is linked to frequency as well. So basically you deliberately induce droop. So what is the droop basically here is that though my generator is isochronous, that means the RPM should not change with the change of with the change of load. Normally, like main engine is not the isochronous. Main engine means, so by the way, before I go further, what is the RPM controlling device here? RPM controller क्या है? What is RPM controller?
Governor.
Governor. So I want to control the RPM using governor. In main engine, we also have a governor, but then we see that there is a change in RPM, because in the main engine the governor is not isochronous. That means it can vary, or the RPM can vary, but whatever is the set RPM, that should not vary. For example, let's say you're given a full head if you have given, and let's say the full head RPM is 60 RPM. Let's, for example, in one of the ship, full head means 60 RPM. Now with the change of load, this should not change. That means, let's say your ship is loaded or unloaded, or you're getting wind from the behind or wind against you. Load may change, but then the RPM is set 60, it will maintain 60. This is the work of governor here. So governor, what is governor doing? Whatever is the set value, the governor will try to maintain that in the main engine. In case of generator, we have a fixed speed. Let's say in the generator case, we have a fixed speed. So let's say the fixed speed is, let's say number of poles is 10. frequency is 60. So what is the speed as per calculation? Quickly, we can do it. Is 120 into 60 hertz divided by 10 poles. So this comes to 720 RPM, isn't it?
Yes, sir.
So usually the generators are of 10 poles are run at 720 RPM. Meaning what? Meaning that if you give 720 RPM, it can give you 60 hertz frequency. If you do not maintain 720, then 60 hertz will not be maintained. Then where does this droop concept comes in? Well, this comes in when you deliberately induce a funda here. That is,
Sir, can you repeat again this concept of droop?
If the load changes, that is load here, and let's say, or load, you can take it on x-axis, load, and let's say this is RPM. Here it is NS, and it is 0 here. Load is 0 here, and then load could be 100%. So what you were saying, that when the load is there 0, that time you may be at certain RPM, but as soon as load starts to increase, your RPM should drop. Your RPM should drop. If it doesn't drop, if this is a case number 1, then you can say droop is 0. If in the case number 2, it's some droop. Droop is X%. So what does it mean? That means you deliberately want a situation that when RPM, when the load increases on generator, that time the RPM should reduce. Not too much, but slightly you want reduction. You want the reduction in the RPM. When the load increases, the RPM should drop. This is the droop actually we're talking about. This should not be too great, but there's a set drop that you want to have. Now, why is this important? Well, this is important because when you run the 2 generators, if you do not have the droop, you can't balance them. For 2 generators to come in parallel and be stable and while running, then the droop is important, because they can share the load. If the droop is not there, they cannot share the load. So here we're talking about the frequency.
Sir, why droop is needed for sharing loads?
Why droop is needed for sharing load? So that's another question. Okay, then you can understand this way. Suppose there are 2 generators which we want to run in parallel. One is the red one. Another is, let's say, the blue one. So the scale of blue is 0 to 100% load here. This way. Blue is this way, increasing this way, and the red one is increasing 0 to 100%. That means this way. So this is the RPM at 0% load. RPM at 0% load for the red generator. Let's say red one is A1. And this is finally what it comes to, this level. And the blue one, which is, let's say, it's A2, auxiliary engine 2. This is what happens at 0% load and when it comes to 100% load. Okay, so this is slightly swept. We'll just draw again 0% load and then 100%. The point of intersection decides actually the load sharing that they will be having. First of all, droop is basically the percentage drop in the RPM when the load is changed from 0 to 100. Okay. When the load is changed from 0 to 100. So how much percentage of the RPM that will be dropping? Suppose here this one is 3% droop. So in the red one, so there will be drop in 3% of the RPM. And in case of blue one, let's say it is also 3%. And because of law of symmetry, they will be intersecting at them in the middle, exactly in the middle. That means they will be sharing 50% load. At any given time, they will be sharing 50% load. All right. Now comes to the layman sort of an understanding that why droop is needed to maintain to share the load. Well, if the droop is not there, then suddenly the load can be taken up by one generator completely, which may risk another generator suddenly shedding its load, or even maybe going on the reverse power situation. So if we want to explain the layman how the sharing of load happens, well, you can share this way. Suppose there are two springs. They both want to share a load, share a weight. This is situation number one, and this is situation number two. In this case, these loads, they are of wire. They are simply straight wires, which doesn't expand or give way to the load. That means they are very rigid. So this is case 2 and this is case 1. In both the cases, load is same. W weight, the weight is same. Now let me tell you, in case 2, there's rigid wire, let's say stainless steel. Both are trying to hold the load. So in this case, case number 2, is there a guarantee that they will share a load all the time? Because one wire may be slightly longer than another wire. Okay, let's say the red wire is shorter and the blue wire is slightly. Let's say red wire is 5 meters, 5.000 meters, red one, and the blue one is 5.001 meters, the blue one. Meters. This is the meters. So in this case, though they are all almost same length, everything is same, but you tell me which one will take the load in this case. Case number 2. The wire that is shorter. If they are absolutely rigid and they don't expand at all. So expand at all means when the load changes, they don't expand, means in case of generator RPM doesn't change at all. It remains the same. It is a known fact that the generator which is at higher frequency, or the one that is actually have a tendency to run faster, will take the more load. Okay. In this case, we're talking about they're sharing the load basis their length. The one with the shorter length will take the load other one will not take the load. So Jack, you tell me in the case number 2, which wire has tendency to take load in this case?
Sir, the red one.
The red one, because the red one has already taken the load. It is not even expanding. So by the time load is required to be shared by blue, it is not there. It says I'm already long enough. Why would I take? Tell the red one to slightly expand it to my length, and then only I should be able to help the red one. Otherwise, I'll not. Let's now take the case 1. Okay, so in the case 1, even then the length initially is the same as 5.000 and the blue one is 5.001. My red one ko I'll just make it with red color so that everybody doesn't get confused. Okay, in this case, in case number 1, tell me if the red is 5.000, but it is a spring. It's a spring. So when the load comes, will it expand? Yes or no? Simple. Jack.
Yes, sir.
So if it expands with the load, it expands. Will now it is the load is coming on the blue one. If the red one is expanding, the load will come to the blue one. Now.
Yes, sir. The both will be equally shared.
Yeah, equal or not equal, that will be depending upon which spring is more rigid. The one which is more rigid will take more load, isn't it? Just imagine the situation. There are 2 springs and one is very flexible, another one is rigid. So if you put the 2 spring in a load, the one which is flexible will keep on expanding, and the one which is rigid will take up the more load than the flexible one. In that case, if they're equally flexible, then they will share equal load. So this is the same concept with the droop. First of all, droop is needed because you do not want one generator to be rigid enough. Hey, I will not change the RPM. If the load is more, let it be. I will keep my RPM high. So other generator will say, hey, you do not want to drop your RPM? Fine, I'm happy with the situation because the one which maintains higher RPM will take the more load. So the generator which was ready to reduce its RPM with the load is happy to give the load to the other one. You take the load, I will not take the load. Simple. But if both of them are like this, that okay, if you load me, I will expand, or the generator which is loaded more will reduce the RPM. So one with a reduced RPM will give the load to the other one. Then the other one RPM also reduces. It'll say, no, my RPM also reduces. You take something. So they keep on giving the load to each other. Finally, there will be a balance. This is same like 2 people with a bucket. Let's say Ram and Sham, they are going with the bucket. So they're sharing the bucket load, and the one which is lowering its hand will give the load to the other one. So other one, if he doesn't lower his hand, then he's ending up taking the more load. This is the same example. Is this a point understood, Jack? And others?
Yes,
Sir, I have just small doubt. So why RPM will decrease just because of increasing the load? Because increasing the load means we are consuming more current from the stator, right? So if we are consuming more current, then voltage will dip, right? So to get the voltage, RPM has to increase now. Why it is decreasing?
Okay, first of all, in the beginning I said it is deliberately induced feature. It is not natural feature with this governor. You deliberately induce this feature with the governor. That means when the load increases, the RPM has to decrease a bit. So if you understand the working of this governor in the generator, there's a droop mechanism given inside the governor that when the load is more, then it automatically reduce its RPM. So that is given already. Now coming to your for another question, another part, you said if voltage should reduce. Well, yes, voltage also dips, and this is another concept where that there must be voltage droop also. But the voltage droop is inbuilt into the voltage controller, not the governor. Governor is maintaining the RPM, is responsible for maintaining the RPM. So the droop, speed droop is part of governor. However, okay, what is a voltage controller, guys? What is the name of controller of the voltage here?
AVR.
AVR. So the droop, voltage droop will be inbuilt into the AVR, and that is also deliberately added feature there. That means the one which is having higher load, the voltage will slightly be reduced, so that reactive load will be shared actually equally. Active load can be shared because when we're talking about load here, this load is an active load. So this is, those who know, we're talking about the kilowatt here. So though you can manage kilowatt or active load using governor and its droop feature, because it is focusing mainly on frequency. But there is one more load in the system, because we ultimately are managing kVA, so which is this one. But there are two parts of that load. One is kilowatt and one is kVAR. And this theta is basically cos theta is the power factor, which is 0.8 in case of our systems. So there will be definitely there will be some kilowatt kVAR load also, which is nobody talks about generally. Nobody talks about this one. So this one is shared also between the generators, and they don't share it equally till the voltage is equal. If the voltage is before paralleling, if the voltage is different, okay, after paralleling, speed and voltage, they have to show same. Both of the generators, they have to show same, because they are now already connected. I'm talking about before they are connected. If the voltage was not same, the generator with a higher voltage will end up taking more reactive load, even though their kilowatt load may be same. This is the concept here. So kilowatt load may be same because RPM is same, or before paralleling the frequency was same, right? Kilowatt, that is reactive load, will be shared equally only if the before paralleling the voltage was same. And that is the job of AVR, to maintain the voltage to be same in both the generators all the time, before and after paralleling, which is for 40 volts before and after. If there is a difference, let's say generator 1 was 442 and this one is 338, that means there is a difference of 4 volts. That means if this is AE1, this is AE2, AE1 will take more reactive load. So if you ask me, reactive load sharing, let's say total reactive load was, let's say 100. Okay, if this was 100, maybe it will share 53, and this will be sharing. I'm just taking examples, 47. So that is the reason, if the reactive load on AE1 is more than AE2, this can lead to more current on AE1. More current on AE1. So you will see that on the panel, kilowatt is correctly shared, both the generator, both the AEs. Let's say AE1 and AE2. You have equal kilowatt sharing, maybe, let's say they're sharing this load equally, let's say 500 kilowatt. This is also 500 kilowatt. And if they're sharing equally, that means their speed droop is same, and the set value of the RPM same between the two generators. But if the kVAR is not shared correctly, let's say it is 53, this is 47. This means that I can imagine with the situation that AE1 will have more current, which, let's say, you will experience 1200 amps here, and here you may experience, let's say, not 1200 by the way, let's say you experience 750. You can calculate by the way yourself. Let's say 850 current amps. Here you will experience 800 amps. This could be the situation. So आपको KVR की value direct नहीं दिखेगी. You will not see the KVR value directly. You will see the current on the panel. You can see the current on the panel. You can see the kilowatt on the panel, and you can see the power factor on the panel. So power factor you will see for A1, since the KVR is higher, so its power factor 0.8 se kam hoga. That will be, let's say, 0.75, and here this may be 0.85. So this may be the situation. Now looking at the situation, you can come to know. So I can imagine what is happening. Both generators are sharing equal load, kilowatt, but their power factor is different, and their current is also different. That means the one which is carrying higher current, it is sharing more kVAR load. So possibly, if I run the two generators unloaded condition, let's say I'm generator 3 and A1 and A2 is running idling, is on an idle load, basically no load at all, then I will realize that A1 voltage was higher. So you have to correct that voltage. Let's say it is not 440, it is, let's say, 443, and it is showing 438. So this was the reason of imbalance in the current and power factor, and the KVR load sharing will be different. So how do you balance it? You, in the offloaded condition, you make this 440 to be 400 again. How do you do it? There is a trim pot given in the panel. There is a potentiometer, which we call trim pot, in the panel. Open in the ECR panel, MSB panel, open that, make it 400 again. With the A3 also, A2 also, make it 440. A1 440, A2 440, and once they're both 440, then you're sure then when they will basically run, they will maintain that.
Sir, one doubt, sir.
Yeah.
Sir, actually, by using this trim port, we are adjusting the exciter field current, right?
Yes.
Okay, sir.
Yeah. So there is one more setting inside, that is droop setting, which, see, nobody touches that. So it will always be, it is factory set. So imagine that it was actually correct. The droop setting that was there, that no, if nobody tempered, that should be no problem. Trim pot is basically, it's a set value. You're changing the set point of the voltage. And where is the trim pot for governor? Well, the trim pot of governor is not hidden. It is outside only. When you said governor increase, decrease button. So if there is a knob there and you say plus and minus. So this is itself doing the increase, decrease of the governor set value, which in case of voltage, it is hidden inside of the panel, and it's done by the trim pot. Both does the same work. They change the set point of the parameter. In case of governor, it changes the set point of the RPM. In case of trim AVR, it changes the set value of the voltage.